Okay, last week I tried to show you the different types of direct shear tests of rock joints. For the soil mechanics, we use the direct shear test to derive or to obtain the collision and friction angle using direct shear test. For soil mechanics, we were trying to apply a constant normal load. If we care about the slope stability problem or slope stability issues, if the rock tends to sliding down, then the normal load will not change during sliding. However, if you have a tunnel like this, and if this rock tends to sliding down, then this condition will be a little bit different from this, because here and here you have very strong constraint. When the rock sliding down, no normal displacement allowed. It is not really a constant load, but the constant displacement, or actually is be the constraint displacement. Sorry, I forget again. I should stand here using mouse. So we will have some special design for the direct shear test of rock joint like this. This kind of testing will constrain the normal displacement. So this kind of test will be similar to this. So there is a case just between this and this. If you have a rock bolt applied to here, then when the block trying to sliding down, then you will have a certain displacement. It's not really constant load. It's not really the constraint normal displacement. It will be in between. During this kind of test, you will have a testing condition with the so-called constant stiffness. The anchor will have their stiffness. Every structure will have their own stiffness. So under that condition, we can try to control the displacement. How to control the displacement? We were trying to use the serve control system, 伺服控制系统，就可以用来做这种所谓的 constant stiffness 的这样子的实验。So for the rock joint test, it will be more complicated than the soil mechanics. Then direct shear for soil. This curve shows you a series of curves during the direct shear test of discontinuities. This part will be the normal displacement subject of the joint subjected to the normal stress. So the vertical axis will be normal stress. Horizontal axis will be the displacement. So in the very beginning, when you don't really have any normal stress, the displacement will equals to 0. Then with increasing normal stress, the normal displacement start to increase. That will be kind of like this, two blocks. And we apply a normal stress, then the displacement will start to increase. In the very beginning, the increasing speed will faster. With increasing normal stress, the rate will become lower and lower and lower. It means when you compress a joint, in the very beginning, it will be closed very fast. But it will become difficult and difficult, more difficult. So here will be the normal stress versus normal displacement. And here, this part will be the shear displacement versus shear stress and shear displacement versus normal displacement. If the first test, we apply a normal stress equals to A, can you understand? If we have a direct shear test and we apply a constant load, like the direct shear test for soil, then this will be the stress strain curve. Shear displacement versus shear stress. For this curves, the A here, we apply a normal stress equals to A. So the beginning, the initial vertical displacement will be A. Because you apply a normal stress, you will have a normal displacement equals to A. The joint will be closed, be compressed to A, from 0 to A. So it will be start from A. Here will be opening, and here will be close or closure, joint closure. So for this curve, you can find very clearly when you apply a shear displacement, then the normal displacement start to opening. The joint start to opening when you apply a shear stress. Okay? This will be kind of dilatancy, shear dilatancy. Goes up to this point, the normal displacement will go back to 0. Above to this point, the discontinuity will keeping dilate because of the shearing. Do you still remember the asperity? If you imagine the joint is many asperity, when you shear it, it will be climb up. Alright? So that will be dilation. So you can imagine when you apply a shear displacement, the vertical displacement will start to increase. But gradually, it will be approached to a constant. Normal dilate. Because of the asperity can be gradually degraded or shear off. So the roughness will become smoother and smoother. The joint will become smoother and smoother. So the dilatancy, the tendency for dilation will decrease. Okay? And we apply a larger normal stress equals to V. Okay? And the normal displacement during you apply the normal load, the normal displacement equals to V. So, how about the shear displacement versus shear stress? This will be these curves, this solid line. You can see the peak strength will higher than the peak strength when the normal stress are lower. Okay? With higher normal stress, you will have a higher shear stress. It will be naturally, you can imagine. So the peak stress is like this, and the residual, the peak strength is like this, and the residual strength is the same. This will be the shear displacement versus dilation. It will be almost the same with the normal stress equals to A. In the very beginning, when the normal stress applied to this joint, the displacement goes to V. And when you start to shear it, the joint start to dilate. So you will have the shear displacement versus normal displacement curves like this. It will be the same when the rocks start to have a shear displacement. The joints start to dilate. Goes up to 0.2, then the shear displacement goes to 0, and the normal displacement keeping increase. But the increasing rate start to decrease when the shear displacement is large enough. If you compare this and this, you can find this. When the normal stress increase, the dilation trend will be suppressed. Okay, it's not so significant, like this or like this. When the normal stress increasing to C, then the dilatancy decrease more significantly. When the normal load goes up to point D, if you have this normal load, then you can see the dilation will be totally suppressed. It still have dilation, but it cannot go back to make the joint open to exist the original compression. Okay, so you can see for the small normal load, you will have very strong shear dilatancy, but for high normal stress, the dilatancy trend is not so significant. Okay, as I tell you, this will be similar to the shear dilatancy for granular soil. For granular soil, you will have a strong shear dilatancy if your confining stress is low. When you have a high confining stress, then the shear dilatancy will start to decrease because of the confining stress confinement. Okay? Any question or any problem with this? Okay. I will show you two more stress strain curves here with the showing here in the dashed line. If we shear the joints with the constraint displacement, this will be the shear displacement versus shear stress, where we make the shear normal displacement equals to 0. Okay? It means during shear, we constrain the normal displacement. It tends to open. It tends to dilate. But we constrain it like this. Like this. We constrain the dilation. Okay? If we constrain the dilation, then of course your normal displacement will remain your normal displacement will remain a constant. Okay? How about the shear stress versus shear displacement? The curves will be like this. You can see the dashed line will intersect with the shear displacement versus shear stress under normal stress equals to A, here equals to A. And you can find the path of the dilation will be 0, 1, and 2. And you can find this point will intersect with the constraint normal displacement point 1. And here we're identical to the normal displacement equals to 0, 0 be 0.2. It means if you shear discontinuities without normal stress in the very beginning, because you constrain the normal displacement, right? When you shear it, the normal load, the normal stress start to increase when you don't really apply any normal stress in the beginning. Understand? So when it goes to this shear displacement goes to this location, the normal load start to equal to the normal load of sigma n equals to A. So you will have the same strength here. Here will be you shear the discontinuities, you continuously shear the discontinuities. and you still keeping the normal displacement equals to 0, goes to this shear displacement, you should have a very large dilation. But because you constrain the normal displacement, so the normal stress already increased to sigma n equals to V. Okay? So I want to show you this different testing condition. The testing condition of this and this testing condition of this will give you different stress strain curves and different strengths. So you can imagine for rock mechanics, like this condition and like this condition, the behavior of the shear displacement versus shear stress of discontinuities could be quite different because of different boundary conditions. Okay? I already mentioned this to you. Okay? So if you don't really have the asperity for joints, and all of the mechanical behavior of discontinuities is only controlled by friction, no asperity, then if you apply 0 normal stress, you will have a 0 shear strength. If you don't have any roughness, you can imagine this, right? Or we always say, if the confining stress equals to 0, then soil will not really have any strength if it is the granular soil without cohesion. Okay? I already explained this clearly in the first slides, so I will skip this. Okay, I already introduced this Barton model or the JRC-JCS model to all of you. I will not spend more time to explain this equation. And I will skip this as well. I already mentioned this to you. What I want to mention to you will be the so-called scale effect. If you have large discontinuities, then the stress strain curve, this will be the shear displacement, and this will be the shear stress. I hope you're already familiar with this. The curves were like this. If you have a small joints like this, then you will have a more brittle behavior like this. So the scale will influence the mechanical behavior of discontinuities. With larger discontinuities, with larger joints, the peak stress, the peak strength will become smaller. Although the residual strength will almost identical. Okay? So that will be the scale effect. And this shows you the scale effect on the mechanical behavior of discontinuities. This will be the this will be the largest discontinuity. And this will be the smallest discontinuities. Color shows here will be the contribution from different mechanism. The white color will be the contribution of strength from the basic friction angle, from the mineral, from the basic friction angle. And this part will be the contribution from the asperity, from roughness. If you still remember me, this will be the 5B, and this part will be the I, roughness I. I already shows you phi plus I concept, right? If we go back to this, this will be the so-called phi plus I concept. This will be the phi, and this will be the I. I will be the roughness. And the JRC will start from 1 to 20. So it means if this equals to 1, then the contribution of the roughness will from 1 to 20. Okay? You will have additional friction angle contribute from the roughness of the discontinuities. And you still remember, if this decrease from 1 to 0, then the contribution of the JRC will decrease from 20 to 0. Okay? This will be kind of weighting the contribution from the asperity. If you have a very large normal stress, then the contribution of the roughness will decrease. If you have a very small rock strength, wall strength, then the contribution from the roughness will also decrease because it is easily to shear off. You cannot really have the roughness surface. When you apply a shear stress or you have a shear displacement, all of the severity will gone, will disappear because of the weak stress or the high normal stress. Okay? So this will be kind of weighting to control the contribution from the roughness. If we come back to here, this will be the contribution from phi R or phi B. And this will be the contribution from the asperity. We will have we will partition separate this contribution from asperity, separate into two parts. This part will be the contribution will disappear after a long shear displacement. Okay? As well as for this, there will be the same, this will be disappear part. Okay. I hope you still remember this will be the small discontinuity, small joint. It will be this. You can find this part will disappear. Then the left contribution from the joint friction angle and the asperity will be the white one plus black one. So the total strength will still larger than this size, larger than this size, larger than this size. Okay? So that would be to explain, you can using this to explain why or how the scale effect occurs. Because of the different size, you will have a different shear off proportion. You will have a different degradation of your roughness. Then you will have a different proportion of the strength still remain. Okay? 所以这个图解释了说为什么你会有就是这个尺度相依的这个力学行为。所以这个是最小的节理最大的节理。那这个白色的通通都是基本摩擦角，然后这一个加上这一个就是它的 roughness。但是这个 roughness 并不是在你剪位移的时候通通都能够留下来，都能够存活，有一些会不见。那所以对于小的这个节理而言，有这些会被剪掉。对小的而言，它其实相对而言，你的尺度越小，它的 roughness 其实就越大。OK， 然后这个随着你的节理增加，虽然你的 roughness 比较小，大的尺度的 roughness 比较小，但是其实你在剪的时候，你被剪掉的其实也没那么多，所以导致了你最后的这个 peak strength， 你会看到小的节理的 peak strength 特别大，大的节理的 peak strength 特别小。所以这样子的一个概念可以去解释为什么你会有 scale effect， 为什么不同的尺度的节理你会有不一样的这个力学行为。I will not try to tell you how to make the scale effect how to correlate the scale effect into the JRC JCS model. I will skip this. But Barton, they proposed a full spectrum to discuss how to consider the scale effect on his Barton-Bendis model. Okay? That will be very important because in situ, in a real problem, in a real engineering, in rock engineering problems, you do need to consider the scale. Different scale give you different mechanical behavior, so you need to consider the scale effect. And the bottom provide the scale effect, how to make the correction of the scale effect to estimate the strength of the discontinuities. I will skip this. You can easily assess and you can easily find the reference or find the material in your textbook, so you can read it by yourself. Okay, then how about the joint with inferiority? Generally speaking, the joint with inferior material, the failure envelope will between the clean discontinuities and the fill material itself. It will be in between. Okay, roughly, the infill material will be the failure criterion will be the lower bound, and the clean rough joints, the failure criterion will be the upper bound. If you have a clean joint with infill material, the strength will in between. Okay, they will be very logic, you can imagine. And generally speaking, the stiffness and the strength of the fill material of the fill joints will decrease with increasing thickness of the infill material. The thicker the infill material is, the lower the stiffness and the strength. OK， 就是这个填充的材料越厚，它的强度跟变形性，它的强度跟它的净度就会越小，或变形性就会越大。OK， but always tighter than the fill material alone, because I say it will be in between. Either one it will be the upper bound and the other will be the lower bound. And if you shear the discontinuities with infill material, then you can find the mechanical behavior will have a two part, which can be separated into two parts. The first part will be the shearing only the infill material. And the other part will be the shearing of the discontinuities. You already have the asperity and the asperity contact. Okay? When the shear occurred, maybe in the very beginning you only shear the infill material. But when the shear displacement goes up to a certain value, then the asperity will start to contact. Then you will enter into another part. Okay? Sometimes the shear strength and the stiffness of the discontinuities with infill material is not really necessary. It depends on the thickness of the infill material. Okay? Sometimes it's not. If you have very strong asperity contact, it will be not. Okay? And we always care about the so-called high swelling potential clay, like the montonite. 蒙多土是一种膨胀性粘土，它通常具有非常低的强度，而且它会有膨胀压力。如果你要是在你的这个 discontinuity 里头有 montonite， 你要非常的小心。Okay? If you have the high swelling potential clay spill inside your discontinuities, you need to watch out. You need to carefully to treat this kind of discontinuities. Okay? And this will be some simple model to describe the stress strain curves of the discontinuities. This will be kind of simplification. What is this? You can go back to this idea. If you already understand this, this will be normal stress, and this will be the normal displacement. If we plot the normal displacement on vertical axis and the normal displacement on horizontal axis, you will have this results. This will be the joint closure. In the very beginning, you will have a zero joint closure when you have a normal stress equals to certain value. When you increase the normal stress, the joint will start to close. And when it goes up to certain value, it will become decreasing and decreasing. So this will be kind of model. You know, model will be some kind of simplification to approach the real phenomenon. So this, the real case will be curves, but not two straight line. But this will be kind of model, simple model. This will be the same things. We can assume the discontinuities of rocks will be the perfect elastic plastic materials. So in the first part, you will have a linear relation between shear displacement and shear stress. There will be elastic behavior. And when your shear stress goes up to certain critical value, there will be the shear strength of the discontinuities. Then the shear strength will keep as a constant, no matter how large the shear displacement is. When you decrease the shear stress, then the curves will going down, unload curves will like this. So there will be, again, it will be elastic. So you will have a loop like this, loading, plastic, unloading to here, plastic again, and unloading. Then you will have a loop. So always we try to use this kind of simple model to make some calculation. Okay? If you cannot try to use this to make the calculation, you need to make it simplified. You cannot use this to do your calculation. If you do need have the full stress strain curves, it is too complicated. So we will simplify this into, say, straight line goes up and the horizontal line. That will be kind of elastic plastic model. Okay, I hope you can understand what I'm talking about. So this will be kind of model of discontinuity, including strength and deformation. Okay, this in soil mechanics we frequent, or also in rock mechanics, we always need to have the constitutive law or constitutive law or constitutive equation to make the calculation for finite element analysis or finite difference analysis. Numerical simulation, we always need to have the constitutive law. So this will be the kind of constitutive law of discontinuities. Okay, so this will be the real case, loading, unloading. And this will be a famous model proposed by Barton Bendis. So this will be a curve. They trying to use the hyperbolic function to describe the loading, unloading of the discontinuities, where it will be the relation between the normal stress and the so-called joint closure. So you can imagine when you apply a normal stress, the discontinuities start to close, and more, but when the normal stress goes up to certain value, the closure rate will start to decrease. It will become more difficult to make the discontinuity close. And when the normal stress keeping increase, then finally we will attain a maximal joint closure. All of the space gone, all of the space disappear. So you cannot compress it anymore. Okay? So there will be the maximal closure. So we try to use the maximal closure and this initial stiffness. This will be a curve, and you can get a tangent line here. If you have this tangent line and you have the maximal closure, if you have this parameter, you can fully describe the normal stress versus joint closure, like this. This will be a hyperbolic equation. According to Professor Tian, I did not check it. In your textbook, this equation have some problem. This one will be correct. Okay, so this equation describes the relation between normal stress and joint closure. And you will have two parameters, A and B. The A and B will be solely function of the initial stiffness and the maximal joint closure. That means you will have the parameter and you can predict the behavior of the discontinuity subject to normal stress. 你有了这个 bottom bandis model， 意思就告诉你说，你可以做预测。预测什么呢？我给你一个正向应力，你就可以预测那个节理会关闭多少。所以这就是一种那个模型模式。Okay, and this will be some empirical relation to shows you how to derive the initial stiffness and the maximal joint closure. According to Bendis, he did a lot of experiments and he gets some empirical equation like this. That means if you have the JRC of the discontinuities and you have the JCS of the discontinuities, and the E0 will be the initial aperture. If you have the initial aperture of the discontinuities, you can observe it in situ. If you measure the JRC in the field, and if you try to get the JCS, there will be the wall strength, right? You can use meter hammer, you can try to use the point load test, or you can do in the uniaxial compression test. Then you will have JCS. If you have a JRC, JCS, and the E0, then it means you can get the curves. Okay? The relation between the normal stress and joint closure. This will be the some of the essential or important parameters for many applications. For example, if we care about the groundwater flow, then we care about the joint aperture. Because you still remember, the groundwater flow were proportional to the cubic of the joint aperture. It means if the joint aperture became 10/10 of the original joint aperture, if you apply a normal flow, normal stress, then the joint close, you will have a joint closure. In the very beginning, it's 1 millimeter. After you apply a normal stress, it will became 0.1 millimeter, for example. Then it became tenths, 1/10, right? 1/10. How large the groundwater flow ability reduce? It will be 1 to 1,000. 它变1/1000，因为你的流体流动的能力是这个内宽的1000，是这个内宽的3次方。We call it cubic law. So sometimes you need to estimate the joint closure when you apply under certain normal stress. You need to quantify it. Okay? So if you have this equation, and this equation will be function of KNI and VM, will be the function of the initial aperture and the maximal joint closure. And here shows you the maximal joint closure and the initial stiffness will be function of JRC and JCS. Of course, it will be also function of the initial aperture. So that means if you have a joint roughness, JRC, and if you have the JCS, you have everything. Okay, so this will be kind of different from the soil mechanics. For soil mechanics, we usually did a lot of laboratory tests. For rock mechanics, we relies a lot on some field measurement, like JRC and JCS, and we trying to estimate everything. Okay. for the global mechanical behavior is still a very large challenge. Also, we already have the ability to make some good model to describe the mechanical behavior of discontinuities. This will be some example. If you have 1, 2, 3, 4 joints only, if we know the mechanical behavior of the joints, then what will be the mechanical behavior of this kind of rock mass? This figure shows you the anisotropy of the behavior. Horizontal axis will be the alpha. Alpha will be the angle between the maximum principal stress or differential principal stress between the direction of the maximum principal stress and this direction. So for this will be 0, and it will rotate clockwise. Rotate clockwise. You can see under 35 MPa confining stress and 140 MPa and 275 MPa, you will have the anisotropy strength like this. An anisotropy strength like this. Okay, I will show you what this means. Why you will have the result like this. You will have several curves. 1, 2, 3, and 4. These 4 curves will be the strengths along this discontinuity, this discontinuity, this discontinuity, and this discontinuities. And this solid line will be the envelope of the lowest part for the failure of this kind of rock mass. You can see the compressibility of this kind of system. Even you can well control the behavior along this discontinuity, 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 discontinuities. When you're trying to predict the mechanical behavior of the rock mass, you still have a lot of challenges. Okay, that will be something I want to tell you. Okay, so you have the homework for the chapter 4 and the problem 7 and the problem 8. How many times left for this hour? It's on time or it's not? 对不对？对不对？还有3分钟。I think we can stop here, okay?